So, last time we were together, we stared right into the heart of quantum weirdness, right? We saw particles being in two places at once, those spooky connections happening faster than light, and even ghosts passing right through walls. It felt like reality itself had a few bugs. But what if those bugs aren't bugs at all? What if they're actually features? What if we could take all that weirdness and use it? Well, that's exactly what we're diving into today, as we witness the dawn of the quantum revolution.
And this right here, this is our theme for today. We are officially moving on from the why of the quantum world to the what now. We're taking all that spooky action at a distance, the stuff that drove Einstein nuts, and we're turning it from a cosmic puzzle into a very real human superpower.
Okay, so let's quickly reopen our quantum toolkit from last time. First, we've got superposition. That's a particle's ability to be in many states at once. Then there's entanglement. That unbelievable invisible thread connecting two particles no matter how far apart they are. And of course, tunneling, the trick of just phasing right through a solid barrier. These aren't just cool ideas anymore. They're the actual blueprints for our future.
So here's our roadmap. First, we're going to build a quantum brain, a computer that literally thinks in possibilities. Then, we'll see how to forge an unbreakable code, one protected by the laws of physics itself. After that, we'll send a cosmic courier using quantum teleportation. And then, we're going to discover that nature has been a quantum genius all along. And finally, we'll stand at the dawn of the quantum age. Let's get into it. First up, the quantum computer. This is probably the most famous piece of tech to come out of this whole strange new world. And you have to understand, this isn't just a faster computer. It's a machine that doesn't just follow logic. It operates on the very principle of uncertainty itself. Its greatest strength is that it thinks in maybes. Let's start with the absolute basics, just to make sure we're on the same page. Your phone, your laptop, they all think in bits. And a bit is like a simple light switch. It's either on, a 1, or it's off, a 0. That's it. It's a world of black and white. A quantum computer, though, uses something called a qubit. And a qubit is way more like a dimmer switch. Thanks to superposition, it can be a 0, a 1, or this beautiful fuzzy blend of both, all at the same time. It lives in that gray area, that haze of pure potential. So this qubit is the heart and soul of the machine, because it can hold multiple values at once. A computer with just a few qubits can explore millions of possible answers to a problem simultaneously. But the real magic, the secret sauce, is when we entangle them. When you entangle qubits, they stop being individuals and they start acting like a single, powerful, interconnected system. You nudge one, its partner responds instantly. That teamwork is what gives a quantum computer its almost unbelievable parallel processing power. Now, actually building one of these things is, well, it's incredibly hard. There are a few different approaches. Companies like Google and IBM use these tiny superconducting circuits that have to be chilled to temperatures colder than deep space. Others, like IBM Q, literally trap single atoms with laser beams. But they all face the same huge challenge: keeping the quantum state stable. It's called coherence. The best way to think of it is trying to protect a soap bubble from even the slightest breeze. You have to keep it perfectly isolated from the outside world just long enough to get your answer. And if you ever got to see one, you would be totally surprised. Forget a sleek laptop or a neat server rack. A quantum computer today looks like a giant, upside-down golden chandelier. It's this gorgeous, intricate mess of wires and tubes, all designed to do one thing: keep its brain colder and quieter than anywhere else in the universe. So yeah, not exactly portable. You won't be taking one of these to Starbucks anytime soon. But here's the kicker. All of that massive, room-sized equipment, that whole golden chandelier, it's all just the life support system. The actual quantum processor, the brain of the whole operation, is tiny. We're talking smaller than your fingernail. It's just an absolute marvel of engineering that something so small needs such a gigantic machine just to function.
Okay, so is it all just hype? Is it worth it? Well, in 2019, Google announced they'd achieved quantum supremacy. Their Sycamore processors solved a specific problem in 200 seconds. And as you can see here, they calculated that it would have taken the world's most powerful supercomputer at the time, IBM Summit, 10,000 years to do the same task. Now, let's be clear, this isn't about raw clock speed. The quantum computer didn't just think faster, it thought differently. Instead of trying one path to the solution and then the next and then the next, it explored every single possible path, all at the exact same time. It's the ultimate parallel thinker.
Now, this incredible new computing power, it comes with a pretty terrifying side effect. A big enough quantum computer could, in theory, break almost all of the encryption that protects our modern world. I mean, everything, your bank account, government secrets, all of it. But here's the beautiful poetic paradox. The very same laws of physics that create this massive threat also provide the perfect defense. Welcome to the world of quantum cryptography. The solution is called quantum key distribution, or QKD for short. And here's the brilliant part. All of our current encryption relies on math problems that are incredibly hard to solve. QKD, on the other hand, relies on laws of physics that are literally impossible to break. The whole thing is built on one simple core principle. In the quantum world, the very act of looking at something changes it. Let's walk through the most famous method. It's called the BB84 protocol. Imagine a sender, Alice, trying to send a secret key to a receiver, Bob, using tiny particles of light, photons. First, she sends a stream of these photons, each with a random quantum spin or polarization. Second, Bob, on the other end, measures each photon he gets, but he uses one of two random filters to do it. Third, they get on a regular phone line, totally public, and they just compare which type of filter they used for each photon. They don't share the result, just the setting. Fourth, they only keep the results for the photons where they both, just by chance, use the same filter. That becomes their secret key. And here's the genius part. If a spy, we'll call her Eve, tries to intercept and measure a photon, the act of her measurement will change its state. It's unavoidable. Alice and Bob will immediately see errors in their final key and know, for a fact, that someone is listening in. The spy is instantly busted.
This analogy is just perfect for it. It really is like trying to send a secret message written on the surface of a soap bubble. The very instant someone else tries to touch it to read it, pop, the message is gone. But more importantly, the sender and the receiver know for sure that somebody was trying to snoop. With quantum cryptography, any attempt to eavesdrop leaves behind undeniable fingerprints. It is physically impossible to hide. And the deep physical law that makes this all possible is something called the no cloning theorem. It's a fundamental rule of our universe, and it says you cannot create a perfect, identical copy of an unknown quantum state. So a spy can't just copy the photon, read the copy, and send the original on its way without being noticed. The universe itself says, nope, you can't do that. In today's security, you're trusting math. With this, you're trusting reality itself.
And I want to be clear, this is not science fiction. This is happening right now. The theory was first proposed way back in 1984, but by 2017, China's Micius satellite was making quantum encrypted video calls from orbit. And today, all over the world, banks and defense agencies are testing and building out their own QKD networks. The race to build a truly unhackable quantum internet has already started. Okay, take a deep breath. We're about to get even weirder. The word teleportation probably makes you think of Star Trek, right? People dissolving into glitter and reappearing somewhere else. Quantum teleportation is
Well, it's both more subtle and honestly even more profound than that. We're not moving matter. We're moving pure information in the most bizarre way you can possibly imagine. And this is the central question we have to wrap our heads around. If I teleport the quantum state of a particle from my lab here on Earth to a lab on the moon, does a photon or an electron physically travel across that empty space? And the answer, incredibly, is no, nothing travels. And yet, the information arrives, perfectly intact. So, how on earth is that possible? The secret ingredient, once again, is entanglement. Let's break down the recipe. First, Alice and Bob create an entangled pair of particles. Let's call them A and B. Bob takes his particle, B, and flies to the moon. Alice stays on Earth. Now, Alice has a third particle, C, whose information she wants to teleport. So she performs a special measurement that links her entangled particle A with particle C. This measurement gives her two simple bits of classical information, just a 0 or a 1. She then sends that information to Bob through a normal channel, like an email. When Bob gets the email, he uses those two bits as instructions to perform a specific operation on his particle B, and the moment he does, his particle B instantly transforms into a perfect replica of what particle C used to be. The information has been teleported. But here's the absolute mind-bending twist. When Alice made her measurement back on Earth, she destroyed the original state of particle C. It's gone, forever. It's like a cosmic fax machine where the original document is shredded the instant the copy prints out on the other side. That pesky no-cloning theorem holds true again. The universe lets you move the information, but it absolutely forbids you from having two identical copies in existence at the same time. Okay, so for a complete change of pace, while we humans have been struggling away in billion-dollar labs trying to build these delicate quantum machines, it turns out that nature has been using these tricks for billions of years. We're only just now beginning to realize that the most sophisticated quantum devices on the planet might actually be alive. This stuff is absolutely jaw-dropping. Take photosynthesis. When sunlight hits a leaf, the energy uses superposition to explore every possible path through the plant's cells at the same time, instantly finding the most efficient route. That's why it's nearly 100% efficient. Certain enzymes in our own bodies use quantum tunneling to make biochemical reactions happen. Without it, our metabolism would just stop. There's even a theory that our sense of smell is quantum, that we're detecting the specific quantum vibrations of different molecules. But if there's one example that just completely blows my mind, it has to be bird navigation. A European robin has a special protein in its eye. When light hits it, it creates a pair of entangled electrons. The Earth's magnetic field affects these electrons differently depending on which way the bird is facing, creating a pattern that the bird can literally see. It's a visual overlay on top of the world that points north. It navigates using a built-in quantum compass. Just let that sink in for a second. Nature has been using quantum entanglement for millions of years. We're the ones who are just catching up. So where does all this leave us? We've designed quantum brains. We've forged unbreakable codes. We've sent information via a cosmic courier service. We've even discovered that nature itself is a master quantum engineer. We are standing right on the edge of a shift in technology that's just as profound as the invention of the computer, or maybe even fire. The quantum age isn't coming anymore. It's here. I think this really captures the shift perfectly. For all of human history, our technology has been built on the rules of classical physics, a world of certainty, of clean logic, of cause and effect.
We are now entering an era where our most powerful technology will be built on the strange, fuzzy, probabilistic rules of the quantum realm. We are, in a very real sense, upgrading our planet's operating system from logic to uncertainty. And with that, our three-part journey into the quantum realm comes to a close. We started with the bizarre foundations, we wrestled with the deep paradoxes, and now we've arrived at the incredible technologies being built from them today. This has been our Quantum Fortnight, but this story is so far from over. The next chapter isn't some distant dream. It's being written right now, in labs all over the world, one qubit at a time.
Which leaves us with one final and I think profound question. For the first time in history, we have the tools to engineer reality at its most fundamental level. We can use the very fabric of space-time to compute, to communicate, to create in ways we're just beginning to imagine. The question is no longer if we can do it. The question now is, what will we choose to build? Thank you so much for joining me on this journey.